Okay, so now let's prove this theorem. This is a characterization of basic forms. On a principal bundle. So, and the group has to be connected. Pi is a principal G bundle. Then a form omega upstairs is basic if and only if it's horizontal. That means IA bar omega is 0, and it's invariant. That means the Lie derivative is 0 for all vertical vectors. So, and you get all vertical vectors from the fundamental vector fields. Okay, so that's the theorem. In one direction, we've done it already. A basic form is horizontal and invariant. So, done. Okay, so now we want to prove the other direction. So suppose IA bar omega equals 0, and the Lie derivative of omega is also 0 with respect to all vector field, all fundamental vector fields. Now, for a connected Lie group, we proved already that if the Lie derivative is 0 for all A in the Lie algebra, then it's invariant, right? So since G is connected, omega is G invariant. Right? So that we know. Okay? And so we have to show that it's basic, and that means we have to find a form downstairs. Okay? So, so pick a point downstairs, and then pick K vectors downstairs. Okay. And we want to define a form downstairs. And the way we're going to do it is we pick any point P upstairs above M. So pick a point P upstairs, and then pick any K vectors upstairs such that they project down to the WIs, okay, for all I. Then we can define a form downstairs, define tau m of W1 to WK to be Yeah, we have a form upstairs, right? In the theorem, we're given a form upstairs. Yeah. And so we have that form at P, and then we evaluate it on V1 to Vk. Okay? So to every k vectors downstairs, you get now a number. Mm-hmm. And it's going to anti-commute, right? So it is a k form. Okay? And so this gives you a form downstairs. Okay? Now, what do you have to show after you make this definition? You see, this then says that omega, then omega is equal to the pullback. Right? Because this is tau m of the push forward and so this is the pullback of tau at P sorry, this is a push forward of the V's. So it's the pullback of tau V1 to Vk. Okay? So I have produced a form downstairs so that omega is the pullback. That means omega is basic. Yeah? Okay. Now, can I stop here? Like, am I finished? Let's say if you were me and you were grading this proof, so would you give this 10 out of 10? So why not?
You didn't use that two condition.
Oh, yes, I didn't use the two conditions, but I have found a form downstairs. So that omega is the pullback.
This is well defined.
Yeah, you have to show that it's well defined, right? You have to show that, well, it should, what if I pick a different point P? I mean, I might get something different. Or what if I pick different V's? I might get a different number, so maybe this is not well defined. We have to show that it's well defined. Okay, then we'll be done. Yeah. You know, I'm grading your homework, but it takes a lot of time. Because sometimes you miss a few things, you know. You don't justify everything. Yeah. So I have to read very carefully to make sure that you didn't forget anything. I'll give it back on Monday. Yeah. Okay. So, yeah, we need to show two things. We need to show that tau is independent of the choice of the VIs and P. Mm-hmm. Okay? So suppose V1 prime is another vector upstairs such that it projects down to W1. Okay. And that's also pi lower star of V1. Okay? then V1 prime minus V1, then pi lower star of V1 prime minus V1 is 0. So V1 prime minus V1 is vertical. And that means V1 prime minus V1 is equal to A bar P for some A bar, so for some A in the Lie algebra, okay? And now you use that first condition. So since iota A bar omega is 0, so omega at P of A bar P V2 Vk is 0, and that means omega P of V1 prime minus V1 V2 Vk is 0. So omega P of V1 prime V2 is equal to omega P of V1 V2. Okay? So this proves that the definition, where is the definition? Here is the definition. Yeah. So this proves that this definition, I put the star there, that definition is independent of the choice of V1. Okay? And in the same way, you can prove that it's independent of the choice of V2 and V3 and Vk. Okay? So similarly, for Vk, V2 to Vk. Okay? So it doesn't depend on the choice of the arguments upstairs, as long as they project down to the W's. And then, now suppose you choose another point, P prime, in the fiber above M, what can you say about P prime and P? You now have 2 points above M. You now have 2 points above M. Yeah, because the group acts freely and transitively on each fiber, right? Each fiber is G. So the group will take this to this. This is PG. Okay? Then P prime is equal to PG for some G in G. And then, so then call P prime. So let V1 prime, to Vk prime be tangent vectors at P prime that project to the W's, then omega at P prime, V1 prime for Vk prime is omega at Pg V1 prime to Vk prime, and that is let me see. Omega at Pg. Omega is invariant. So omega is equal to Lg star of omega. Okay? At Pg. So because omega is invariant, is G invariant. Right? Because we're assuming that the Lie derivative is 0 and the group is connected, so omega is G invariant. And that means, so this is no, just a minute. This is not quite right. No, this is not quite right? Yeah. So, okay. I think, what do I want to say? Yeah, so like P goes to PG by right multiplication. Oh, sorry. Yeah, this isn't right because on a Lie group, the action is on the right. So I should be using right multiplication. Okay? So, so omega at Pg will pull back to omega at P. So actually, I think I really should be doing this, right? I should be right multiplying by Rg inverse, okay? So omega is Rg inverse of omega. Let's see. Rg inverse will take Pg to P. So this is Rg inverse of omega at P. Yeah, because P, yeah, P is Pg G inverse, right? Yeah, that's right. Okay, so this is omega at P. Apply to, then you push forward. Okay. Yeah. Now, but these are vectors that push down to the WKs. V I prime is equal to, if you right translate and then you project, that's just the same as projecting. And so you get WI. So this expression is independent of these arguments, right? So we have okay, so this, now I'm going to say it is, what would be a good symbol for that? Okay, that is equal to omega p of V1 prime to Vk prime. Because those are also vectors that project down. Let me see. No. This is a P. So a P is V1 to Vk. Okay? Yeah. Since these are also vectors that project down to the W's. And yeah, so that says that the definition, this definition, right, is independent of the choice of P. Okay? So the definition of tau in star is independent of the choice of P in the fiber. Okay? Because if I choose a P prime, I get the same answer. Okay? Okay, so that says it's well defined. That's omega is pi star of tau. Let me say, thus tau is well defined, and omega is pi star of tau. Okay? So it's basic. Okay. Yeah. All right, so for the rest of the hour, I'm going to discuss the ring structure on the cohomology of the total space of a fiber bundle. That's part of the Ray's theorem, but I didn't tell you about it before because, well, it's such a big theorem, I tell it to you in parts so that it's easier to digest. So now in a spectral sequence, E2 has a product structure. It's just a tensor product. And that product structure will induce a product in all the other ERs, right? Because all the other ERs are quotients of subspaces of the previous one, right? Because you're taking the kernel, that's a subspace. The kernel of the ER is a subspace, and then you take the quotient by the image of the dr. So every time you do that, you still have a product structure. Okay? You have a subring, and then you have a quotient ring. And so that product structure will persist all the way to E infinity. Okay? So E infinity has a product structure. And the Ray theorem says that E infinity is the associated graded module of the cohomology of the total space. Okay? And so the associated graded module also has a product structure. Okay, so here we are looking at a fiber bundle. With fiber F. And now let's assume that cohomology is with coefficients in any commutative ring with identity. Now, so as part of the Ray theorem, there is a filtration on the cohomology of the total space. Oh, yeah, no, I think, no, I'm supposed to go to that blackboard. So, here. Okay, so there's a filtration, right? And then the associated gradient is E infinity, but there's more than that. So that there's a filtration so that multiplication in the cohomology of the total space induces a map from Fk cross Fl to Fk plus L. So the multiplication in cohomology kind of respects the filtration. And from this, it follows that let me see. Fk cross Fl plus 1 is going to go to Fk plus L plus 1. And Fk plus 1 cross Fl goes to Fk plus L plus 1. So that means you have a well-defined map. Therefore, there is an induced map from Fk over Fk plus 1, cross Fl into Fk fk plus L over fk plus L plus 1, right? Because this part, it goes to 0. And you can also divide by fl plus 1 there. Okay? Yeah, because like here, this is in the kernel of this map, so you can divide it out. And then this is in the kernel, so we can divide it out. So you have this. And these are the terms in the associated gradient. So this is the product structure on the associated gradient. On the associated gradient of the cohomology of the total space, which is the direct sum of fk over fk plus 1 for all k from 0 to infinity. Okay? Yeah, so that makes the associated gradient into a ring. And the theorem is that, well, E infinity is a ring, and so is the associated gradient of the cohomology. And these two rings are isomorphic. Okay? So they are isomorphic as rings. Okay, so what does this mean? This means that when you use a spectral sequence to calculate cohomology, if you can calculate E infinity, then you know how the equivalence classes of cohomology in this associated gradient multiply. Okay? And then you have to try to figure out the ring structure, you know, from how the equivalence classes multiply in here. So let's look at an example. Let's look at U2. So cohomology ring. U2. Okay, so U2 acts on C2 by multiplication, and it preserves the Hermitian inner product, so it preserves the sphere. It preserves the unisphere S3 in C2. Now, okay, now let's try to show that the action is transitive. So suppose you have 1, 0 there, that's in C2. Okay, that's in S3 in C2. You view these as complex numbers. And then you have another point here, AB. Okay? What is a unitary matrix that will take this point to this point? Yeah, so like we can complete AB to an orthonormal basis, right? A, B, C, D for C2, okay? If it's an orthonormal basis, then when you put them together, you get a unitary matrix. Then A, B, C, D is in U2, okay? And A, B, C, D times 1, 0 is AB. So there's a unitary matrix that takes 1, 0 to any point. Okay? Now, how do you show that if I have 2 points, that there's a unitary matrix that takes this to this? Yeah, you can take, there's a unitary matrix from here to here, and there's one from here to here. So the inverse will go from here to here, and then here to here, okay? So given another A prime B prime in S3, so there exists A prime, which is a unitary matrix, such that A prime of takes 1, 0 to A prime B prime. Then, then A prime inverse will take A prime B prime to 1, 0 and then to AB. Okay? So that says U2 acts transitively on the sphere. On S3. Okay. And then we need to calculate the stabilizer of a point. So the stabilizer of 1, 0 should take A, B, C, D. A, B, C, D should take 1, 0 to 1, 0, and that implies that A is 1, B is 0. So if A is 1, C has to be 0, because the rows are also orthonormal. Okay? And that means A, B, C, D has the form 1, 0, 0, D. Okay? And this has to be a unitary matrix, so D has to be a complex number of unit length, so it's in U1. Okay? And U1 is the same as S1. Okay? And yeah, so that's the stabilizer of a point, and therefore by the orbit stabilizer theorem, U2 over U1, the group over its stabilizer is diffeomorphic to an orbit. The orbit of a point is S3 because it acts transitively. Okay? And since U1 is a closed subgroup of the Lie group, U2, when you have a closed subgroup, then there's a fiber bundle. U2 maps to S3, and the fiber is U1. Okay, and so now we can calculate the spectral sequence, and it works because S3 is simply connected. Okay. If the base is simply connected, then E2 is the cohomology of the base tensor with the cohomology of the fiber, which is S1. Okay? So here is the E2 term. Okay, the cohomology of the base is here, and the cohomology of the fiber is here. So the cohomology of S1, right, it has a generator X. Okay? I'm now using integer coefficients. These are. And then you have a y here. And so the tensor product, you have a y tensor x, which I'm just going to write as xy. Okay? And then it's 0 here. Well, you see, B2 yeah. So D2 is going to take this to here, and D3 will go here. Yeah, so they're all 0. All the differentials are 0. Mm-hmm. Okay, so okay, so therefore E2 is equal to E3 is equal to E infinity. Okay. Now, and I know how they multiply in E infinity, because this xy, it multiplies to x times y is xy, which is a generator in dimension 4, right? Okay, but that only tells you how the associated graded module multiplies. So this is G as rings. Okay. Now, so I'm going to put a bar here because now in E infinity they are not really cohomology classes, but they are classes in this, right? So this is so these classes, they are equivalence classes in the quotients. Okay? So I put a bar there to indicate that they are equivalence classes in here. And now I have to figure out how they multiply in the cohomology ring. Okay? So let's look at in dimension 0, well, H0 of U2, it's just Z, is generated 1. It's connected. I mean, if you have a 1 here, that means it's connected, right? And then H1 of U2, so it has a, oh, I'm sorry, yeah. My filtration, I think I should write it like this. F lower k of k plus 1. Okay? The filtration in cohomology induces a filtration in each degree. So in degree 1, I have F10. Okay? It contains F11, which contains F12. The top degree is the degree of the cohomology. Okay? And it's, I have two quotients. Okay, so this is 0. Right? And then these are the two boxes. These two boxes. So this box is Z x bar, and this box is 0. Okay. Now that means, well, that means that F11 is 0. Yeah, so F11 is 0, and then F01, which is the cohomology in degree 1, is Z x bar. Okay? So this says that x bar is actually not an equivalence class, but it's actually in the cohomology. Okay? Since x bar is actually in, okay, we'll write x is equal to x bar. Okay? Now, in some other examples, you see, if this is not 0, then x bar would be an equivalence class. You know, and then it would be different from x. But here, it's the same as x. Okay. And then, oh, okay. And then, like, you see, it just turns out that, like, in this example, when you go down degree 2, it's 0. In degree 3, you have only one thing that's not 0. In degree 4, you have only one thing that's not 0. So in this example, all these classes are actually, all these equivalence classes are actually in the cohomology. So y bar is actually in H3, and x bar, y bar is in H4. So we can write y is y bar, okay? And x bar, xy is actually x bar, y bar, okay? You're taking equivalence class by 0, okay? And so yeah, it gives you the ring structure. So the cohomology of U2 is Z1 plus ZX plus ZY plus ZXY. And it tells you how things multiply here. The generator x times the generator y gives the generator xy in degree 4. So this is the free algebra free exterior algebra generated by x and y. Okay. So in general, the free exterior algebra generated by some elements, that means you write down all possible products, and the relations are xi, xj is -1 to the degree of xi times the degree of xj, xi. Okay? That's a free exterior algebra generated by a number of elements. Okay? And now you can generalize this example to higher dimensions, but in higher dimensions, then sometimes you see, then you get something like 1, x1, 0, x3, x1, x3, say in degree 4. Okay? And to figure out where this goes, you use the fact that it's an antiderivation. So this is dx1, x3 plus minus x1 dx3. Okay? So if you know that x1 goes to 0 and x3 goes to 0, then this will go to 0. Okay. So it's going to be actually quite easy. I think all the differentials are all 0, okay, for un. Okay, and then you figure out the product structure the way I did this. Okay? All right, so we'll stop here today. I think on Monday there's a problem set due, right? Yeah. It's funny. Yeah, we are only a quarter of the way through. We are, because there are 9 weeks, so that's 36 lectures. And today I finished lecture 14. We are about a third of the way through. All right, yeah, okay. Okay, good, yeah. So there will be 2 more problem sets. Let's see. Yeah, okay.